this was a perfect entry to bring us in the mood of what we are trying to do, but also to accompany us into a second contribution now, that because this event is really going, it's really multidisciplinary, it's going to be a more highly scientific contribution by theoretical particle physics, physicist and cosmologist Lisa Randall from Harvard University. We have been, especially Ivana, of course, reading her book, Warped Passages, Unraveling the Mysteries of the Universe, Hidden Dimensions, and being fascinated about her way of accompanying us in these extra dimensions that apparently are invisible, and as she says, are not yet named, they don't yet have a name. And we want to actually try to also state with the contributions that are coming later, that maybe these dimensions have been already having a name and are having a name, and other cosmological traditions as well. Just briefly, Lisa, just to introduce you to our audience, I'd like to share your bio. So your research connects theoretical insights to puzzle in our current understanding of the properties and interactions of matter. Lisa has developed and studied a wide variety of models to address these questions, the most prominent involving extra dimensions of space. Her work has involved improving our understanding of the standard models of particle physics, supersymmetry, baryogenesis, cosmological inflation, and dark matter. So it connects also to Monica talking about us as being in darkness and being the darkness itself. Professor Randall earned her PhD from Harvard University and held professorships at MIT and Princeton universities before returning to Harvard in 2001. She's also the recipient of honorary degrees from Brown University, Duke University, Bard College, and the University of Antwerp. So she's actually someone we're very proud to have as one of our guests. Lisa, the word to you.
Okay, so first of all, thank you for having me here. It's definitely a little bit outside my wheelhouse, although I have done things with artists. And I have to admit, I mean, it's interesting because I am definitely coming at this from a somewhat different perspective. I mean, I love the title, Limits of Perception, but the question is, how do we address it? And we can address it by saying that scientific methods might not work, or we can address it by saying scientific methods haven't been developed yet that can accommodate all the invisible things so far. And I think this is a big confusion people have when they think of science, because a lot of the time, scientists tend to present things perhaps as more definitive than they are. And other people tend to resist the idea that science will expand to incorporate other ways of thinking. But so I'm just going to give a couple of examples of the kind of work I do. I know a lot of people are doing performances, but my performances are in fact talks. That is what I do. So to the extent that I perform, teaching and talks. So I'm going to give some idea of the kinds of things we've been thinking about and how we as scientists try to address these issues. That's not to negate the role of art. I think art is very eye-opening and expanding and makes us look at things in a different way. I also really love the poem that was read in the beginning, the Adrienne Rich poem, because it is true that as individuals, we still are participating in the scientific community, and there is a whole society out there that we have to deal with. That doesn't change the fact that science can hopefully address some specific difficult questions. And one of the really important goals of scientists is not just to explain what they know, but also to understand what they don't know. I mean, that's the key, to understand what you don't know and how to get beyond that. And so I think in that respect, we all share some opinions. Okay, so I'm just going to start. This is a little busy, but I just want to remind you the other thing I guess you all know, but the universe certainly extends beyond what we see. And that's true for scientists, it's true for everyone. There are just, when we look around, a lot of the time as a scientist, you come up with ideas about the substructure of matter or even what's going on in the far reaches of the universe. And people will say that doesn't make sense, it's not intuitive. But our intuition is very much guided by the limited wavelengths over which we actually literally see things. Now, I mean, the genius of science, to some extent, has been to extend those wavelengths so that we can see much smaller scales and much larger scales than we previously been able to see. But that doesn't mean that there isn't an enormous amount that we cannot observe. And furthermore, obviously, we only see things that interact with light. There might be other ways of detecting them. We might be able to detect gravitational effects, for example. But when we talk about seeing things, we're talking about seeing things with light in a particular range of frequencies. And that is necessarily limiting. It doesn't mean other things don't exist. And as scientists, we're fully aware of that. But sometimes people get caught up in it because it's so beyond our intuition. And I'm not only going to be talking about a couple of exotic ideas, extra dimensions of space and dark matter, which is perhaps exotic, but it's necessarily there, as I'll try to explain. But a lot of the time, the history of science, or the history of physics at least, in the more recent past for sure, has been developing tools to probe different scales, and then realizing that physics at those different scales doesn't necessarily work the same way it did at larger scales or smaller scales, or whichever it is that we understood before. So being able to access new regimes makes a big difference. And you can find things that seem crazy from the point of view of the scales we see, but are completely consistent at scales beyond those we observe. And one of those things is, in fact, literally extra dimensions of space. We can use extra dimensions metaphorically. There can be many other dimensions. But one of the things really is looking in dimensions of space beyond the three, which you can think of as the X, Y, and Z axis, or latitude, longitude, forward, backward, up, down. I mean, there are three that we observe, but that doesn't mean there can't be others that have so far avoided our perception. And we'll talk about how that could happen. So when I talk about extra dimensions of space as a physicist, I'm talking about dimensions that might truly be there, but they're everywhere. When I say there, I mean they're everywhere. It's just they're too tiny for us to even notice their effects. Or, as I'll explain, they could be so warped in their effects that we, again, don't notice it. So how should we think about these extra dimensions? If we want to think, if we acknowledge that our visual capacity wasn't designed to see more than 3 dimensions, what can we do? Well, we can basically reduce it to lower dimensional things. So we can look at slices, for example. Now, even though a slice would be 2-dimensional or lower, so let's imagine a slice of 3 dimensions, even though it's 2-dimensional, if you put it together, if you have many slices, you could reconstruct the full 3-dimensional object. And similarly, in higher dimensions, maybe there are 3-dimensional slices that you can put together to construct higher dimensions. So that gives us something that we can think about, but then we have to remember that there's many cases. So this is the example from Flatland, where a sphere passes through a 2-dimensional surface and we see slices, but they all add up to a sphere. Another thing is projections. You can have a projection. That is to say, again, you can have some higher dimensional object, but we only see the lower dimensional projection. And again, any single projection will not capture higher dimensions, but it's conceivable you can put them together to capture higher dimensions. And this projection is a joke, because I don't know if those of you who've done this, but the standard thing is to make something that looks like a rabbit that projects to be, so you have a hand, you make a hand motion and you project a rabbit. In this case, the rabbit's projecting a hand. But either way, you're clearly losing information by looking at a single projection. Oops, sorry about that. Okay, holograms are another way. You can have interference that captures higher dimensions. One of the things we might do as a physicist, if I'm trying to understand something, is say, you know, all the 3 dimensions that we see are basically identical. So I don't need to draw them. I could just draw one of, And then it allows me to have freedom to draw one dimension that represents 3 dimensions and one that represents higher dimensions. Or what we do in effect, without even trying, is average them. If you can't detect them, we'll just average over it. And you just don't see any effect from it. So they might as well not be there. So even though they might be there, if you can't have this definition, the resolution to see them, they don't have any effect. But I have to say, the best way is in many ways, math or words, not pictures. And when I say not pictures, I mean not pictures that are literally higher dimensions. You who are artists out there can do your pictures metaphorically in other ways. But just if I try to draw higher dimensions, it usually just looks very confusing. Okay, and that's just extra dimensions generally. What about extra dimensions in physics? Why do we think about it? Well, if the idea first was proposed in physics, I mean, people have been thinking it in math for a long time, and people argue that philosophers have been thinking about them for a long time, but probably in a different way. But Kaluza proposed extra dimensions in 1919. And there's no reason that can't be there. Einstein's equations of gravity actually work in any number of dimensions. There could be these dimensions. But there's a big question, which is, why are the extra dimensions different? Why do we only see 3 of them? And it's actually an interesting story. Einstein was the referee of the paper and actually rejected it for a while until Klein figured out a way that extra dimensions can be different. And I'll tell you a little bit about that later. If string theory is right, it suggests there are at least 6 more dimensions. But I'm going to treat the question of if they exist and the number as an open question that hopefully we can eventually resolve either theoretically or experimentally. But if you're very tied to a particular theory, you might have a prejudice about how many dimensions there are. But they're not necessarily even all the same size, for example. But why don't we see them? And this is what I said earlier. Einstein delayed the publication. But what makes the other dimension different? Now, of course, remember I said earlier, we can't draw higher dimensions. So although these are 2-dimensional pictures, they represent 4 dimensions. So if you think of the long dimension as infinite, which it's not in this picture, but if it's infinite, and represents all 3 of our dimensions, and we say there's another dimension, that's the one orthogonal, the small dimension. Now suppose that dimension was curled up. That is to say, I cannot walk an infinite distance like I can in 3 dimensions. I would end up back where I started. And imagine making that tube smaller and smaller in diameter. Eventually, you would just conclude that dimension isn't even there because you just can't perceive it. So basically, his idea was, this is a nice picture, but his idea was that the entire universe is curled up. Everywhere there in space, there is this curled up circle, the way there is everywhere along that infinite line. And that is how the dimensions were hidden, according to the original Kaluza-Klein idea. Actually, a collaborator and I, Raman Sundram, actually found another way that extra dimensions could be hidden. And it's actually because of objects that are known as brains, which are membrane-like objects in higher dimensional space. And they play an essential role in string theory. So the idea is that not everywhere in extra dimensions is the same. Some stuff is actually stuck on a lower dimensional surface. I like to think of water droplets on a shower curtain in your room. Those water droplets are stuck on the curtain, even though you have a 3-dimensional room. And there could be stuff stuck on a brain. And furthermore, that brain can have energy that it itself distorts space and time and makes it look very different. And what we found was this remarkable warp geometry. Just to be clear, this is a brief talk. I'm going to flash some big ideas at you. I don't expect anyone to understand them all. Of course, if you read my book, I do. I'm just joking. I expect you to be able to at least appreciate the kinds of things we're thinking about and the ways we think about them. But there's no way I could actually explain this in enough detail. So if you find it confusing, you should, because they're big concepts that I can't possibly explain fully right now. But back to brains, this is BRANE. They're a higher dimensional world in which particles and matter are stuck in a brain. And again, keep in mind, this is drawn as 2-dimensional, but the ones we live in are probably 3-dimensional if they exist. And again, it should be an infinite. Those 3 dimensions could be infinite. And with brains, and this is just to give you an idea of what we do by thinking theoretically and scientifically. Now, there's a difference between saying we've discovered it theoretically, and we've discovered it experimentally. We don't know if any of these things exist, but mathematically, we have found that if you have brains, there could be a new way to hide dimensions, and even an infinite extra dimension, not necessarily a tiny dimension, but an infinite warp dimension is possible. A new concept of our place in the universe. That is to say, maybe the fact that we see 3 dimensions is very much guided by the fact that we are localized to the region we are, and other places could look different. And we also found a potential answer to a big physics question, which is why gravity is so much weaker than the other forces. So by thinking about extra dimensions and brains and these new dimensions, we've come up with new ideas. Whether they're realized in nature, we don't know, but this is the way science works. I'm going to skip the part about the hierarchy problem because I think it's just too much, because I don't want to go on forever. But I do want to say that extra dimensions, we don't know. The colliders are looking for the effects of these extra dimensions, and I could explain why and how. But it's because we really think that maybe these dimensions are connected to actual things we see in nature. And if that's true, we'll be able to find them. I'm going to spend another few minutes. I don't know how long this is supposed to last, but I'm going to talk a little bit about dark matter too, because that's another way. It's a totally different way that we're dealing with our lack of perception. So here we were saying that we're not going to see the effects of these other dimensions until we go, say, to higher energy scales. In the case, and that's because things might be heavy or so weak, or it could be things that have, you have to reach a certain energy for the effect to be big. Dark matter is really interesting because dark matter is just extraordinarily weakly interacting with our matter. So it could be that dark matter, so first of all, let me say what dark matter is. So our universe, as far as we know, has different components of the energy. The stuff that we actually know about, the material objects that we are talking with, or what we're made of, stuff made of atoms, is only about 5%. The rest of the energy of the universe is detectable through gravity, but so far no other way. So when I said earlier we see with light, this is stuff that we don't see with light. I mean, we see its effects with light because gravity affects other things that then interact with light. But we do not see things directly that are so-called dark. By the way, we do see dark things. Dark things absorb light. It's a really bad word. I think in the German it was a better word because it implied more the idea of mystery. But there's stuff in the universe that interacts with gravity, but not with light. And there's actually 2 different species. The fact that they're called dark is sort of both incidental. They're not necessarily related. One is just pure energy, just spread smoothly throughout the universe. That's actually most of the energy today. Early in the universe, it was a very negligible fraction, but today it's most of the energy. The other component is dark matter. It's stuff that does not interact with light, but does interact with gravity, just like usual matter. So in other words, it clumps together. It's like our matter in the sense that it clumps together. It forms galaxies. It's around us. But it does not have the other forces that are part of the standard model, namely the strong and weak nuclear forces and electromagnetism. It's conceivable it does have a little bit, but we haven't seen any evidence for that yet. So we're just going to treat it like it's just interacting with gravity for the moment, or at least with itself. So that's why I just said before, dark matter isn't really dark. It doesn't absorb light. It should be, it's called transparent matter. In fact, lots of dark matter is passing through you, and you're not completely unaware of it. But because there's so much of it, remember there was 5 times the amount of energy in dark matter as ordinary matter. It's what gave shape to our universe. It's actually really what led to galaxy formation in the first place. So how do we see it, since we don't see it directly? Well, I make a joke in my book Dark Matter and the Dinosaurs that it's like if you're going down the street and you see some crowd and lots of cameras and everything, you know something's going on there. Maybe there's a famous person, but you don't know who it is. And in the same way, sorry, my battery's running low, so I have to find my computer cord, or else I might get cut off. Very late. Let me just Okay, here we go. Sorry, this is a bit of a mess. I just changed the computer screen, so it's a bit of a mess right now. But here we go.
Yeah, okay. And I think anyway, our audience has been yet disoriented and the different kind of presentations, but from Monica to you, and slowly we will get into also a very different presentation. So it's fine. We can make it completely disruptive as it has been. So thanks for continuing.
Okay, so guys, can you go on? Okay, now I'm plugged in, so I won't get disconnected.
Yeah.
Okay, so I just want to, so it's just, again, this is when we talk about limits of perception, I find this really interesting and important. And I'm not going to go into my theory, I don't think, but I do want to tell people how we know about dark matter. Because again, it's one of these things that people who don't do science are like, are you sure you got the equations right? Are you sure you know it's there? But the thing is, the idea that there is matter that doesn't interact with light the same way our matter does, seems to me almost obvious. Like, why should everything be made up of the same stuff that we perceive? You know, we're just human beings. Why do we know about everything in the universe or see everything in the universe? If anything, the thing that I find surprising is that we are as significant a fraction of the universe as we are. There's only 5 times the amount of dark matter as ordinary matter. Could have been 10 to the 12th. It could have been, you know, billions or trillions or whatever. Could have been a very different number. But the other thing that convinces me that this is really true is that we detect it indirectly, but we detect it many different ways. And they all agree. They all agree that dark matter exists, and they agree on the amount there is. So let me just give you a flavor of how we know about it. The very important one is called galactic rotation curves. So in our galaxy, the Milky Way, Vera Rubin made these really famous measurements where she measured how quickly dark, ordinary matter, stuff you see, stars, go around in our galaxy. And the thing is that the speed is determined by what is the gravitational pull, because there's going to be a balance. If they don't have enough pulling it in, if they're going too fast, they'll just fly away if there's not enough gravity. And she found indeed that the stars were moving faster than you would have thought they would. And the reason is essentially, we believe, because there's matter we don't see. So there's more matter that's pulling it in, which is what explains why they don't fly away. And that's also shown to be true of something called galaxy clusters, which are bound states of galaxies. So many galaxies together. And again, they stay together because there's dark matter that holds them together. If it was just the stuff we saw, it wouldn't be enough. There's also some really fantastic measurements done through things called gravitational lensing, where you have some object, and even if it's dark, light can bend around it. And it bends around it in different directions, depending on which direction the light came from. So when you project back, you see either fuzzy images or you see multiple images. And that actually lets you sort of trace where matter is in the universe, because you would see different images according to what's there in between you and whatever it is that emitted light. Another thing that's really important is the cosmic microwave background radiation, which I believe was mentioned in the last presentation, the stuff that was considered white noise at some point. That radiation, it turns out, has now been measured in great detail. And that detail tells us what the universe looked like at a time before structure formed. We get really detailed information. But we also learn about we can also measure from that, because of the structure in that radiation itself, in perturbations, in the density perturbation spectrum. You can actually learn from that how much matter versus dark matter there was. And that number agrees. And then there's something else that I like, because it really makes it look very direct that it's dark matter. There's something called the bullet cluster, which is the merging of different clusters. And in it, you see that ordinary matter gets stuck in the middle, but dark matter continues through, just like you would expect if you had matter that was not interacting. And it's very hard to explain that through some non-conventional theory of gravity. But actually, this is the bullet cluster picture. But actually, the thing that really convinces me that dark matter should be there is the existence of galaxies in the lifetime of our universe. If there were only ordinary matter, structure would not have formed. And furthermore, if there hadn't been matter that didn't interact with light, light would wash away the structure. So ordinary matter had to hitchhike along with dark matter in order for it to form. So this is a great example of something that you might say Well, we don't see it. It's not really there, but it is there. It's just we detect it in many different ways. So the real question isn't whether dark matter exists, but what is it? And I'm not going to go through the rest of the talk. I think I've told you enough science for one lecture for artists on a Sunday evening. But I hope you get a flavor for how we think about these things that seem beyond perception, but might actually be there and affect our world. And in the case of dark matter, does. We just don't know exactly what it is. So I hope this helps with the rest of your day. This is a really fun conference. So thank you.
Yes, thanks a lot, Lisa. It's helping a lot for those who can understand it in this multi-layered perspective, for others, because we are mainly a group of artists and people engaging in activist activities and more poetic paths. I think there is some that can be grasped, absolutely.
I just want to add, I really think there's a lot of room for communication, so I actually really enjoy these kinds of events.
Amazing. That's great. Usually when we talk about dark and black, we always more refer to black matters and dark matters, not matter. But in the case of this exhibition that we are now hosting at Savi, it's absolutely fundamental to try to explore this path and these dimensions that are just not hypothetical. We assume that they are there, and there are many cultures, many ways of knowledges that have been connecting to them. But of course, understanding that from a scientific and highly scientific perspective, so much advancement in the research has been done. It's impressive. And